Hello everyone, this is Emil Naruto. Welcome to my channel. So today I'm gonna teach you all the topics, that are involved in the linear regression. Okay. So first of all, we're gonna look the introduction for the linear regression, and inside this particular subtopic, I'm gonna tell you what is meant by a linear regression and how to build any linear regression model, and what is the process of measuring model accuracy, structure of the linear regression model, and what are all the coefficients that are involved inside the linear regression model, and what is meant by an intercept and what is an error. And then we gonna turn towards uh, ordinary least square method. This is a method which is with which we can build, or with which we can uh, run our linear regression model. So this is one of many methods. So there are so many methods, but out of all those, we're gonna look for the two most popular methods. One of such is the ordinary least squares, and the another one is gradient descent. So this particular method, that is gradient descent, is very much useful. Uh, I mean, it's also very much useful when it comes to the neural networks part in deep learning or any other further studies. Okay, so gradient descent is very much important, and then we're going to look for so these are all the things which comes under the, I mean, mostly which comes under the simple linear regression model. So but then we also have multivariate linear regression model. Okay, and then we're going to look for hypothesis testing in linear regression. So hypothesis testing is nothing but yes, we have already built a linear regression model, and now we're gonna look for is it reliable? Is it reliable in the? I mean, is it eligible to be deployed into the production or not? So for that, if we want to look or if we want to test whether this model is good to deploy in the production or not, for that purpose, we're gonna run hypothesis testing. We're gonna conduct hypothesis testing. So that's what it is. And then I'm gonna tell you what are all the assumptions involved in linear regression model, and what if some of the assumptions or all of the assumptions have been failed to meet the requirements. So in that case, what are all the steps do we need to take to build the linear regression model if some of the assumptions are failed? Okay. And then finally, I'm gonna tell you what are all the pros and cons. There are advantages and disadvantages of all the linear regression model. And then finally, I'm gonna tell you how to, I mean, all the usage of the linear regression, that is on nothing but the applications of the linear regression model. So this is the entire thing I'm gonna tell you under this particular topic, linear regression model. But for this particular video, I'm going to tell you the introduction of the linear regression and then what is meant by linear regression. So for this two subtopics, I'm going to tell you in this particular video. Now just deep dive into this topic. Okay. Yeah. So, so if you look at here, so linear regression, right? So linear regression. So what is meant by this linear regression? Linear regression is nothing but an algorithm. Okay, this is nothing but an algorithm, machine learning algorithm. Okay, with which what we can do using this linear regression, we can predict. Okay, we can simply predict. Okay, no worries, we can predict. But what, I mean, why do we need to predict, and what can we predict? I mean, what do we predict usually? For example, yeah, the stock prices. We can predict the stock prices. We can also predict the US dollar. US dollar value. You can also predict miles per gallon, miles per gallon of a car. So these are all the things. So we can predict all these things. Okay. So this is in general, right? This is in general for any kind of machine learning algorithm. We can predict this. But when it comes to the linear regression part, so what is this particular linear term and what is this regression term in usual? So I'm going to tell you that. So, but before that, I just want to tell you something. Okay, we can, yes, we can predict some kind of things here, right? So we can predict. So this prediction, this particular prediction, it involves some kind of process. If we want to predict something, it may have some kind of process. So what is this particular process? The word, what is this particular process? The process is nothing but the in mathematics, in maths, in maths, it's called a function. Don't worry, I'll explain you the great examples. Like for example, okay, uh, let's say I have some kind of x. Okay, I need to use this particular x, and using this particular x, I need to predict some y. Okay, this is the thing. So what is mean by this x here? X is nothing but my input. Okay, this is my input. Using this particular input, I'm gonna predict some kind of y, which is nothing but my output, right? So the process involved from the right to the beginning of the entering the input to getting the output, this there is some kind of process involved here. This arrow is nothing but some kind of process. Okay, this is nothing but the process here. So this particular process in mathematics we can call it as a function. Okay, so this process is nothing but in maths we can call it as a function. Okay, so this is what it is. So now, uh, so anything, for example, uh, let's say I want to predict some kind of a person who is gonna, for example, we have a certain bank. Okay, we have a kind of bank. Okay, so this is a bank here. Now I have one person. Okay, he has come to this particular bank and he has uh, made some kind of application for his loan, for his loan approval. Okay, for his loan approval, and then the bank will decide whether they should allot this particular person with some kind of loan or they should reject this particular approval or not, based on this particular person's past history. Okay, this particular person has some kind of history. In his history, he might, I mean, he could have taken some kind of loans, or maybe he could have already paid them, or maybe he could not have been paid them. So some of the things has happened in the past really. So this particular bank should verify these particular past details, okay, of this particular person, and then based on this particular past, they will decide whether they should give loan or not. Okay, so here what is our objective? Our objective is just to, our objective, our aim is to predict. Okay, so this is kind of a classification problem basically. So, but no worries. I'll give you another example. For example, uh, uh, what we can call. See, I'll tell you. No worries. Okay. So I won't confuse you, but just have a look at here. Just have a look here. So, for example, we have our stock values, right? We have our stock price. For example, let's say we have some kind of SBI. Okay, we have SBI, and this particular stock. For this particular stock, let's say the stock price, the current stock price is, let's say, some kind of 500. Okay, 500. And now we want to predict the stock price of this particular stock in future, in the coming 2 years. Okay, our aim now is to predict the stock price. Okay, to predict the stock price of SBIN in coming 1 year. Okay, so this is our aim. So for that, if we want to predict this particular SBIN stock price in the future years, in the future coming years, so we are given some kind of data, right? For example, here we are given some kind of data. This data is the past. This data is the past. Let's say past 5 months of data. Okay, from the past 5 months, this particular SBIN is some kind of performing like this or something. Okay, it has some kind of values. Okay, so from the past 5 months, the SBIN stock price is going through this particular uh, chart. Okay, now using this particular, now using using this past history, we need to predict the future. We need to predict the future. What is it? For example, we need to predict in the coming year, this particular SBIN value will remain here, or will remain here, or will remain here, whatever may be there. We just need to predict it. Okay, so this is the future, and this is the past data. So from the past data, from analyzing the past data, and till we get the confirmation about the prediction of that particular stock price in the near future, is nothing but a kind of process. Okay, it's a process. So this process is nothing but a function in the mathematical terms. Okay, this process is nothing but a function in the mathematical terms. So for example, if you say this past is nothing but an x and the future is nothing but a y, so it will just undergoes from past to the future through a process which is nothing but a function. So what is mean by this? This is nothing but the input. This is nothing but the output. Okay, and this is nothing but the process. Okay, so we can also call process as f of something. What is that f of something? Something is nothing but our input. Okay, so f of x, which gives us, if we process this particular input using our process, we will get the output as y. Did you get this? Okay, so this is the thing here. Now okay, well, we have already, okay, for example, this particular f here, what is this particular f? We all know that it's a process, right? We can also call it as it's a kind of model. It's a model here, process or model. Why we are actually calling this particular F as model? Why? Because process is what do you mean by the process? Transforming input to get the output is nothing but a process. So what involves exactly here? Nothing but our model. We need to build some kind of model which takes this particular x value as the input, and it will actually gives the output as the y, right? So this is our model. See here, this is our model, and it will actually takes the x value to give the y value, right? So this is nothing but F is nothing but a process or a model. Okay. So for example, okay, we have already decided to build a model. Okay. For example, we need to build a model. Further, to build a model, to build a model, we need some kind of data. We need some data. Okay, which is nothing but our input. So how do we get the input? How do we get the input? So our input data will always be our sample. Okay. For example, let's say this is the whole population. Okay. For example, let's say I just want to uh, see. For example, this is the whole population of the India. Okay, for example, this is the whole population of the India. So it is almost very much. I mean, it's almost impossible uh, to go to reach out to each and every person and ask collect their opinions. Okay, so instead of that, what I can do is I can just grab some kind of sample from the total population, which is actually representing this particular uh, population, right? So did you get that? So India is nothing but our population, right? It's our population. So we can't approach each and every person in particular and record his opinion. So for that purpose, what we can do is we can just grab some kind of part out of all the population, which is nothing but our sample. So in the model building purpose, we gonna use this particular sample instead of this particular population. Okay. So we will we will use sample data in the model building process. In the model building, which represents the population. Okay, so this particular sample will actually represent the whole India. Why? Because we have taken this sample from the population itself. So this sample will actually represent the whole India. What does mean by that? So what's that particular statement? When we say this particular sample, this sample will actually represent the India. What does that mean? Actually means, for example, we have performed some kind of tests on the sample itself. Okay, see, I'm doing some kind of inputs here. Okay, I'm performing some kind of tests here. So I have got some kind of results here. Okay, we have got some kind of results. These results, okay, these results will actually represent the whole population here. Okay, why? Because the sample data was actually collected from the population itself. So if we get the results from this particular sample, these outputs are nothing but the representation of the whole population here. It's the representation of the whole population here. Did you get that? So that's it. Okay, now okay, I have already told you this is the sample, and this is the whole population. So we have some kind of terminologies here for the sample and the population here. I'll explain you, no worries. Okay, so first of all, this this is the whole thing. This is nothing but the population, or we can also call it as universe. Okay, we can also call it as universe. So out of this entire population, we are actually taking some part. Okay, this some part, this is the minute part, is nothing but the sample here. And one interesting thing about this particular, about this 2 is sample data. Sorry, this sample data, it won't change. Okay, this sample data, it won't have any kind of fluctuations. Okay, this sample data will not be changing, but this, for this universe, that is the, for the population data, it will always be changing. See, the difference between the population and the sample is nothing but the sample will not be changing here, but the universe will always be changing here. That's the basic difference. So for this particular reason, we need to ensure, okay, we need to ensure that our sample is reliable with the population, which is today's trend. So what's the meaning of this particular statement here? So nothing but, for example, I'll tell you. So what's the meaning of this here actually? So what I'm saying is, for example, see here, I want to, okay, okay, in the early 1970s, in the early 1970s, the cost of 1 acre, 1 acre land, 1 acre land in India is equal to, let's say, I'm just saying the rough figure for just for the example purpose. This is not the truth. Okay, let's say some 20 lakh. Okay, some 20 lakh. This is the scenario. This is the scenario in 1970s. Remember this particular uh, date here, 1970s. Okay, so using this data, I want to predict the, okay, I want to predict the land cost of land in 2000. So in fact, the cost of the 1 acre land in India is equal to 20 lakh. This is the data from 1917 to 1980 period. Okay, this is the data for the 10 years period. Now I want to know the cost of 1 acre land for 2022 to 2032. Okay, based on this particular data. So I build some kind of linear regression or some other model, okay, some other machine learning model. Then I'll predict some kind of output here. But let's say here, see here, in the 10 years for the 10 years span of that particular period, that is 1970 to 1980, the cost of the 1 acre land in India is approximately 20 lakh, for example. Now, if I want to predict the cost of 1 acre land in India in the period 2022 to 2032. Let's say my model has predicted that particular cost as some maybe some 40 lakh. Okay, so okay, I have built some kind of model and it has given me this particular output, that is the 40 lakh. Okay, that is the 40 lakh. So is it reliable with the today's trend? So we need to think for that. Why? Because see here, see here, this is the data which is some many, I mean some hundreds of years back, right? So with this, I mean during that that particular period, the price is actually 20 lakh, which is okay at that period. But now, if I want to predict some 2020, if I want to predict the cost of 1 acre 1 acre land in India using this particular data, okay, using this particular data, and I want to predict for the 2022 to 2030 period, which is nothing but a 40 lakhs. So I think this is not the correct scenario. Why? Because see, the data is actually outdated. If you want to predict the cost of 1 acre of land in India during the period 2022 to 2023, at least you need to have the data from 2010 to 2022. This would be the perfect period for you, for your data. But see here, you are actually having the data 1970 to 1980. So this would be the this is not actually the data is not actually reliable with the today's with our today's trend. So what we can do is you will ask that particular client, oh sorry, we could not, I mean we could not actually process your request. Why? Because the data is actually outdated. See here, the data is actually outdated. So just go back and collect the data which is actually reliable with the today's trend. That is nothing but the data should be updated. Okay, if it is in sync with the today's trend, then we can actually uh, predict the price for the coming future. Okay, so the data should be in the data should be reliable with our today's trend, which this is the most important point here. Okay, okay. So now, for example, let's say, see here. Okay, I'll give another example. Okay, so for example, I need to predict the petrol price. I need to predict the petrol price for 5 years, 5 coming years. Okay, for the 5 coming years. Okay, I need to predict it. For example, let's say today we have the petrol price of some kind of let's say 110. Now we can predict the petrol price for the 5 years as that is our model has predicted the price as, let's say some let's say 200. Okay, our model has predicted the petrol price in the coming 5 years would be 200 rupees. Okay, 200 rupees. But this is the prediction. This is not the actual one. Okay, this is the prediction. But the actual scenario is, so this is the prediction, right? Prediction by our model. But we also have some kind of actual scenario here. Actual scenario is nothing but the actual scenario would be in the coming okay the in the coming years the price would be, let's say, some uh, 210. Okay, 210 rupees. 210 rupees. So this is the actual thing. So this is the actual price here. So when you look at the difference here, what is the difference here? 210 minus 200 is nothing but the 10 rupees. So this particular 10 rupees is the difference. So we can also call this particular difference as error. This is the error here. So the error is nothing but the difference between the actual difference between the predicted and actual. Okay, this is nothing but the error. I can also give you the example based on some kind of chart here. See, for example, okay, for example, so this is the 5-year period. This is the 5-year, and this is the 10-year period. So for 5-year period, we have predicted that we have predicted that our price would go for at least 200 rupees. Okay, our model has predicted this. That is, this would be the point here. Okay, so this would be the point. So for 5 years, definitely, so 5 years, definitely, our model has predicted that the petrol prices will definitely go and hit 200 rupees. But in what has happened actually, the price has go crossing this particular value and ended up at some value like this. Okay, which is nothing but the 210 here. So the 5-year, I mean, same, the years are the same. Like for the coming 5 years, our actual price, which has our actual petrol price that has ended up at 210 rupees. So the difference here, see, this is the difference. This difference is 10 rupees, right? So this difference is nothing but the error here. So error is something, you should not say that error is something which is very bad. No, that's not the case. Why? Because error is nothing, that's not a kind of bad thing. That's actually explaining the difference between the your predicted model's value and the actual value. So that's not a kind of bad thing. So in the error, we have, in error, we have some three types of errors. There are three types of errors. So what are they? So the first one is the bias error. And the second one is the variance error. And the third one is the random error. Okay. So these are the three kinds of errors, three different kinds of errors. And now, if you look at here, so we have the control. We only have control over this particular two kind of errors. We don't have any kind of control on this, the random error. Okay, so we can only control either the I mean we can only control the bias error or the variance error. We can just control this. Okay, but we don't have any kind of control on the random error. Okay, but why do we need to I mean why do we need to control this particular bias error and the variance error? Why do we need to do that? I'll tell you. So I'll tell you. For example, see here, the bias error, and the variance error they can't be removed completely. Okay, bias and the variance can't be eliminated completely. Okay, so they can't be eliminated completely. But now what to do? Even though they can't be eliminated completely, but still they can they can be they can be reduced, right? So they can be reduced. What happens if we don't I mean if we don't reduce this particular bias error and the variance error? What happens? I'll tell you, but before that I just want to know, sorry, I just want you to know that if we if we reduce if we reduce this bias error and the variance error, if bias and variance error are reduced, then our model our model will be right fit. So what is meant by this right fit? What happens if we reduce this bias and variance error? Our model will be right fit. What if we don't reduce this bias and variance error? Our model will fall under the two categories. Either it will be underfit, or it will be under the overfit. So what is mean by these two terms, underfit and overfit, which is now I'm gonna explain you. See here, for example, let's talk about the underfit. Underfit is something it performs poor on sample data, and also it performs worst on production data. Production data is nothing but the new data. Okay, so what is mean by this overfit here? So overfit is nothing but the model will just performs well on the sample, but performs poor on production data. Production data is nothing but the new data here. So this is the scenario for the underfit and the overfit. So underfit is nothing but our model will actually performs poorly both on the sample data, and also it performs poorly on the production data itself, which is the new data. And what is meant by the overfit here? Overfit is nothing but the model. Our model will actually performs well on the sample data, but it performs poor on the production data, which is new data. So this would be the overfit scenario, and this would be the underfit scenario. And our goal is not to be in either of the situations, right? We need to be in the situation which is the right fit, model. So we should not We should not make our model to be in either of the situations, that is uh, underfit. We should not, we won't accept this, or we also won't accept this. Okay, we need this kind of right fit model. So if we want our model to be in the right fit scenario, what we can do is we need to minimize this bias, and we also need to minimize this variance as much as possible. Okay, then only our model will get uh, then only our bias and variance error will get reduced, and then finally our model will becomes right fit model. Okay, so this entire situation is known as, uh, if you clearly observe here, so what's happening is we need some kind of, if you observe here, uh, we need we need to control bias comma variance, which is nothing but this is known as bias variance trade-off. Bias variance trade-off. Why? Because if the bias and the variance should never be, I mean, they should never be too low or too high. They should be in a position where, for example, if the bias is very high and if the variance is very low, and also if the bias, for example, see here, this is the bias and this is the variance here. If the bias is very high and the variance is very low, or if the bias is very low and if the variance is very high, the situations may fall in either of the categories, like either it may underfit or it may lead to overfit. But we don't want any of these situations. We never want any of these situations. We only need right fit model. So for this particular right fit model, what we can do is we need to we need some kind of trade-off between the bias and variance. So that is nothing but a bias variance trade-off, right? See here, I have already used one kind of terminology, that is the right fit here, right? Right fit. So here I have used the terminology that is the right fit, right fit. Or we can also say that generalize. We can also say that generalizes well. Okay. So both the terms are absolutely acceptable. Why? Because see here, right fit is, what is meant by a right fit model? Right fit model is the desirable. It's a desired model, right? This model is desirable. Generalizes well means it, I mean, generalizes, that is it won't have any kind of partiality, right? It generalizes very well, that is it's the model which doesn't have any kind of partiality. So this is also the same, right fit also the same. So the model need to be in the right fit or in the, or it should generalizes well. Both are the same, right? Both terms are same. Okay, so now, so here we have different kind of models. We have different kind of models. One such model is we have some decision tree here. We have decision trees, and we also have naive Bayes. Naive Bayes. We also have linear regression here. So all these machine learning models will establish some kind of relation between the input and the output variables, which is nothing but the y is equal to mx plus c. See, this particular equation is considered only when it comes to the linear regression part, right? This particular equation is related to this particular linear regression part. So this, what is this equation meaning? I'll tell you. So here x is nothing but the input variable, and what we get is output variable, that is the y. This is the output and this is the input here. So this equation is actually es- establishing some kind of relation between the input and the output variables. So likewise, our decision tree has also has some kind of approach, that is, it establishes relation in terms of decision rules. But now I don't want to explain what is meant by decision trees right now. Why? Because it would be a separate kind of topic. I'll explain when it comes. Okay, so just look at here. The decision trees will establish some kind of relation between the input and output variables in terms of decision rules. Okay, now if you look at the naive bias, what happens, it establishes a relation between input and variables with the likelihood ratio and prior and posterior probabilities. And here linear regression also, it also establishes the relationship between input and the output variables using a mathematical equation. Mathematical equation, which is nothing but the y equal to mx plus c, this particular equation, right? So if you consider this particular linear regression part, we gonna use some kind of mathematical equation which is nothing but y equal to mx plus c. So each algorithm has their own way of establishing the relationship between input and output variables. But now we are actually in the linear regression part since. So I'm gonna explain what is meant by this y equal to mx plus c. But before that, I just want to say a few things like linear regression predicts. Okay, linear regression will always predicts the output variable in a real number form. In a real number form. For example, it will just example. I'll give you the example here. Like let's say 9.72 or 29,000 or 52 lakh. These are all the numbers, right? These are all the real numbers. So in the linear regression part, the output will always be in this particular format in any of these numbers, like no matter whatever may be the numbers, but they should be the real numbers itself. Okay, and another thing is, in the linear regression, what is meant by the linear? Linear means, here linear means, see this expression, y is equal to mx plus c. Here x is nothing but the input, right? Here y is nothing but the output. Okay, input, this is the input and this is the output. And what is meant by this c? See here, the c is nothing but the intercept. We can also call it as the constant, or we can also call it as bias, right? So what is meant by this particular m here? So what is m here? So what is the m here? M is nothing but the slope here, or coefficient, you may call, or weights. You can also call it as weights. Okay. So whatever may be the values. So what you can call this particular input value, you can also call this particular x as input value, or you can also call it as independent variable, independent variable, or you can also call it as predictor variables. See here, this is the output variable, right? So you can also call it as the response variable, response variable, or you can also call it as the dependent variable. So whatever may be the words, the terminology is actually the different one, but the meaning of this all words is nothing but the, this is y is nothing but the output, m is nothing but the coefficient, and x is nothing but the input, c is nothing but the intercept or constant, whatever you call. So this is the thing. But did you ever wonder like what is the linear? What is the linear here in the linear regression? That's nothing but, see here, linear. See, I'll tell you. Y is equal to mx plus c. Okay. So see here, all the independent variables or all the coefficient parameters are actually, all the variables are actually rising to the power 1 here. Okay, this is the reason why we are actually calling this particular equation with the name linear. Okay, linear. And see here, what is it actually doing here? See, we are actually saying in the shortcut form of y equal to mx plus c, but in reality we do have, we don't have any one single variable here. We may have lot more variables, like for example y equal to mx1 plus mx2 plus mx3 plus and so on plus c here, right? So but these are all the variables which are actually rising to the power 1. So that's why we are actually calling it as, calling them as linear. But also what's actually internally happening here, see, just focus on here. See what's going on here. This particular independent variable is actually multiplying with this particular weight or nothing but the slope. This particular second independent variable is actually multiplying with the slope m. Okay, m1 you can call m2 and m3. Okay, so this particular x3 is actually multiplying with this particular weight m3, right? And all these things are getting added here, which is nothing but the plus sign here, addition. Okay, these are all the variables along with their weights are actually getting added here. So linear regression, so linear regression is nothing but the, linear regression is nothing but, it's a linear in linear regression means, linear in linear regression means that this this method models our data with linear combination, right? with the linear combination. What is meant by this linear combination here? Linear combination is nothing but all the variables are actually rising to the power 1 here, right? So linear combination of variables. What are the variables here? Variables are nothing but the input variables, right? That the independent variables also. Independent variables, which is in the above equation x1, x2, and so on, x3 and so on, right? So there may be a whole lot of variables. All these are the explanatory variables. Okay. So this is the case here. See, I'll tell you one thing, the difference, the basic difference between the simple linear regression and the multilinear linear regression. See here, for example, see, this is, I have only one variable, that is x1, and I am actually, sorry, I only have one variable, that is x, and now I'm actually predicting y. So this would be the straight line here, and so this would be the straight line. This is the example for the simple linear regression model. Okay, simple LR model. Why? Because we only have one input and we are actually getting only one output variable. But in reality, what happens is we may get more than one single variable. That is, this would be our x1, and we also may have some kind of x2. We also may have some kind of x3 here, right? We have these things, and we need to predict the y here. So what will be the shape of this particular model? This won't be a straight line anymore. Okay, it would be some kind of hyperplane here. This would be our hyperplane. Like, sorry for my drawing skills. So this would be our hyperplane here. So that's a kind of structure here. This would be hyperplane here. So what we can call multiple multivariate. Why? Because why multivariate? Why? Because it's having some multiple variables, right? So it's multivariate linear regression model. Do you get that? This is the basic difference here. And do you know why it's actually why it's not the here? Why it is straight line here and why it is not the straight line here? Why? Because see here, for example, if you plot, if you have more than one variables, that is, you have let's say three variables, and you want to plot that particular, model. You want to plot that particular model here. So what you can do, you'll just plot this point like this, but it won't be straight line anymore. But rather than instead of straight line, it can form some kind of scatter here. It would be some kind of scatter here. See, these are the scattered points here. This is not a straight line anymore. See, this is not the straight line anymore, but instead of that, it would be a scattered. Why? Because see, these are all the, it has some kind of there's some kind of variables, right? This is x1, x2, x3, all these things, right? So this would be the scatter here. So this is not a straight line, but instead of that, it's a kind of a hyperplane. It's a kind of hyperplane here. It's a kind of hyperplane. Okay. So why it is actually forming like this? Why? Because I'll explain why it's happening like this. I'll explain. For example, let us consider this is our output, nothing but the y. Let us consider y is nothing but the um, uh, let's say rainfall. Okay, centimeter rainfall in centimeters. So y is nothing but our precipitation, nothing but the rainfall in centimeter level. Okay, and now what is this x1 here? X1 is the temperature, let's say. And what is this x2 here? uh, x2 is the geographical location, let's say, geographical location here. And what is meant by this x3 here? Maybe x3 is some other kind of like let's say what you can call, maybe humidity or something, maybe whatever maybe the factor is. See here, the logic here is, here we only have, we will only get one output, but if you want to get this particular output, you only have these three input, right? These are the only input we have. But instead of that, what are all the factors that are actually deciding this particular rainfall here? Maybe there are so many factors. Maybe there are some, let's say, additional uh, 4 to 5 factors, right? But we are actually we don't have any kind of information regarding these particular factors, that is x4 and x5. So we are actually not considering these two variables in our model here, right? So we are only considering x1, x2, x3, but we are not considering x4 and x5. Why? Because we don't have any kind of idea about these particular factors. So we are not actually considering these two variables inside our model building. That's what the reason. For that purpose, we are actually ignoring some kind of information here. Due to that purpose, we are actually getting some kind of scatter of points instead of forming just a straight line here like this. Okay, so that's the main reason for which we are actually forming the cloud, some kind of a scatter part here, right? But so what can we do? But what if we have, for example, if we have some kind of straight line, we can definitely say that this is some kind of a this is some kind of positive correlation. Like for example, if the for example if the x is increasing, like if the x is increasing, the y will also increase. For example, if x is at this particular point, the y will also at this particular point. For example, if x is at this particular point, the y will also be at this particular point, right? So likewise we can definitely say. But what's actually happening? We are actually getting some kind of cloud here, that is the scatter. So what can we do with this particular point? We should not look at the shape of the particular points. Instead of that, we can have a look at the trend here. See, all the points are actually in the positive trend here, right? So this is the trend here. So instead of looking for a definite shape here, definite straight kind of line or definite shape here, we can think of a positive trend here in this particular points. See, all the points are actually in this particular direction. So we can record that this is a positive, that this is a positive trend. So using this trend, we can capture. So using this trend, we can capture this particular trend and represent this trend in the form of a model. So this is it. So that's what it is, right? So yeah, that's all for today. I think. I think I have already explained enough about what is meant by a linear regression. By this, I think uh, you all had some kind of real good basic idea about what is a linear regression mean by, right? So that's what it is. This is all about the linear regression. See, I'll explain. I'll just recap once again. So this is the linear regression, and which is nothing but the algorithm. It actually predicts the real numbers. It predicts the output in a real number format, right? Nothing but the example is nothing but the stock prices of any kind of stock, or maybe the price of a dollar in the near coming futures, or anything, gallons per, miles per gallon of any car. Okay, what is the kind of distance, that is the miles per gallon of any car. So we can also predict all these things. So how do we do that? That's nothing but that's a kind of process. We are initially given with some kind of input variables, and using all those input variables we need to predict some kind of output variables, which is nothing but input are nothing but the past, and output is nothing but the future. And this involves a specific process, which is nothing but our model itself. The process is nothing but our model itself, right? So here comes the topic of sample and population here. Why? Because this is the population, and out of all the population, we only grab some kind of data points which are nothing but our sample. Why? Because we can't even approach to each and every person of the population. That would be an absolute time waste, and it would also cost you more than just for this particular sample. So instead of going for the population, we'll just consider sample as our data preference for this data, right? So if you want to build any kind of model here, you would definitely need some kind of data, which is nothing but the sample data here, right? So you will need the sample data here. So using the sample data, you can build any kind of model here, but you need to ensure that if our model is reliable with the today's trend or not. For this particular example, for this particular topic, I have already explained some kind of example. Like this is the past data, which is almost outdated, and now using this particular outdated data, we are actually predicting the house prices. We are actually predicting the price of a land in India for this coming years, 2022 to 2032, which would be absolutely bullshit. Why? Because this data is actually got outdated. So there is no sync with the today's trend. So what's the particular suggestion is, which I can give you, is nothing but the data which is nothing but our sample data. It should be reliable with our today's trend. That's what the logic here is. And now I have given some kind of example, that is this is the price which is predicted by our model, but the actual scenario is 210 rupees. So what is the difference here? The difference is nothing but the 10 rupees here, right? The difference is 10 rupees here. That's nothing but our, what we can call it as error. So in error we have three types: the basis, sorry, the bias, and the variance, and the random. We should never have control over this particular random error. We can only control the bias or the variance error here, right? We can only have some kind of control for the bias or the variance error. So what we can do is our aim is to build a model which is of right fit. See here, which is of right fit. Why it is important to have the right fit model? Why? Because if we don't make sure our model is in the right fit condition, there may be a chance that our model will definitely fall in either of these two situations. That is, one is underfit or the out or the overfit. What is meant by an underfit? Our model, after building our model will definitely performs poor on both the sample data as well as on the population data, or nothing but the production data. And what is meant by the overfit? Overfit is nothing but our model will definitely performs exceptionally well on our sample data. That is nothing but our training data. But on the test data or the production data, it will perform very worstly, right? So this is the overfit scenario. Okay, so this is the kind of situation. So we need to make sure. So we need to make sure that our model should not be in either of these two situations, but instead of that, our model should be in this particular situation, that is right fit model. So you can call whatever with the name you want. Like you may call it as a right fit model, or someone will call it as the model which is actually generalizing very well, generalizes. Both are the same here. Okay, but here let's focus on here. So our we should not have the higher variance, higher bias with the lower variance, or with the lower bias with the higher variance. There should be some kind of trade-off between those bias and the variance. That is, it should not be too high or it should not be too low. Okay, they both should have some kind of balance in between them. So that's nothing but the topic here. That is bias variance trade-off. Okay, we need to control this bias error or and the variance error to get the right fit model here. Did you get that? So now I'm going to explain what is meant by linear regression here. Linear regression is nothing but it's a combination of the it's a linear combination of some kind of variables along with the weights that are actually added up, right? So each algorithm has their own way of establishing the relationship between input variables and the output variables. For example, if you look at here, this is the example equation for the which is related to the linear regression. So here in this equation, we are actually establishing the relationship between input and the output variables in an equation form, mathematical equation form. But uh, unlikely, I mean, here in decision trees, it's not the scenario here. Why? Because here the relation between the input and the output variables will be established using some kind of decision rules, right? What do you mean by those decision rules? Decision rules are nothing but like this. For example, I just want to know whether tomorrow will it be going to rain. I mean, will it be going to rain? That is yes. Or will it not be going to rain? That is no. I want to know. See, this is my condition. This is my objective here, right? I want to know. So it may have some kind of decision rules, like, right? If this condition is met, it will have some kind of some other condition. If this condition is met, it may goes to some other decision rules, or if this condition is not met, it may goes to some other decision rules. So this is the example of the decision trees pattern. Why? Because these are actually following some kind of decision rules. But when you look at the naive base, here these are actually following likelihood ratio and prior and posterior probabilities. I'll explain what are all these mean by in the later coming up videos. But for now, since the topic is related to the linear regression, just focus here. The linear regression is actually related to it actually establishes the relation between the input and the output variables using a kind of mathematical equation, right? So we have some kind of things here, like LR linear regression will always predict the output variable in a real number format only. That is, the output should be only in the numbers, right? There should be no categorical outputs here, unlike in the classification, right? So in the linear regression, what is meant by linear? See here, Linear is nothing but all the independent variables are actually rising to the power 1 here, right? See here, mx1, this is nothing but the m is nothing but the weight here. What is x1? This is nothing but the variable. M2 is nothing but the weight here. X2 is nothing but uh, x2 is nothing but the variable. See, all the variables are actually raising to the power of 1. So that's why we are actually calling them as linear regression. And all the variables are actually multiplied with the weights, that is the slope here, m1, m2, m3. All the variables are actually multiplied with the weights, and all of them are actually getting added to our intercept, together forming our output, right? So due to this reason, our model has got some kind of name like linear regression, right? So see here, in y is equal to mx plus c is nothing but the generalized format of this particular equation here. But when you look at here, y is also called as output variable, that is response variable, or you may call it as dependent variable. But when you look at m here, we may call it as slope or coefficient or weights here. X is nothing but independent variables or the predictor variables. C is nothing but the intercept or constant or the bias here, right? So now LR in the linear regression is this is the kind of definition here. It's a linear combination of the explanatory variables. So I have forgot to write this particular word, that is explanatory. Why it's important to write the explanatory variables here? Why? Because see, these variables are actually explained by their weights here. That is m1, m2, m3. These weights are actually explaining how important a variable is in this particular model building process, right? So that's it. And now when you look at here, this is a general kind of scenario. If you build a simple linear regression, you will get some kind of straight line. But when it is of multiple variables, you will get some kind of hyperplane structure instead of the straight line, right? And see here, for example, this is the kind of output, that is we need to predict the how much the rainfall would be in centimeters, right? For that we have some kind of input variables like temperature, and we have geographical area, and we have some kind of humidity and the things, right? We only have three inputs here. So depending on these three inputs, we need to predict the y. But in reality, rainfall is actually deciding. Rainfall is actually getting decided based on two other factors also. But we don't have any kind of we don't have idea about them. Since we don't have any kind of information regarding these two remaining factors, so we are not actually considering them. Instead of considering them, we are actually ignoring those two factors, and we went with only these three variables in the model building process. So due to this reason, our data points are actually getting scattered. These are actually not in a straight line format. Why? Because some information part is actually getting missed here, right? So instead of looking for a kind of a specific shape, which is a straight line shape or for a hyperplane, you need to look for whether this particular object is actually having some kind of a trend or not. See, when you look at here, this particular object is following some kind of positive trend here, right? Some kind of positive trend. So this trend is very important here. We need to capture that particular trend, and we need to represent the trend in the form of our machine learning model, right? So yes, that's all for this particular session. Now I I'll see you in the next video. If you like this content, just please subscribe. I'm actually taking whole lot of efforts to teach you the best content. But no worries. Just don't get confused if you don't have any idea what's going on. Just I'll suggest you to watch this video again. Okay, don't watch this video in I mean with 2x mode, right? You can just watch it. If you want, you can watch it in 1.25x, but beyond that, just don't go beyond that, right? So I hope everything is clear to you. Now I'll continue the series. So I'll see you tomorrow in the next video. Good night. Take care. Jai Hind.